Okay, so this is the video for 5.2. It's the first one. This is just a 5.1 review, which is what we needed to know about eigenvalues. So eigenvalues are a scalar value such that ax equals lambda x for an associated eigenvector. So it's like a special situation where the transformation times the vector is the same as if you're just increasing the magnitude on that vector. And that special relationship creates this eigenvalue-eigenvector relationship. And as I said in class, the eigenvalue is kind of like the heart of the matrix, and it can tell us a lot about the health of the matrix or the behavior of the matrix, just from that little bit of information. If you are given the vector, you can find the eigenvalue or see if an eigenvalue exists by just taking a times x and seeing if there's a value that will give you a scalar version of that. And if you're given the eigenvalue, you can apply it to a minus lambda I x equals 0. Go ahead and do the a minus lambda I, and then set it equal to 0 in a homogeneous system and solve for the eigenvector. And provided that it's solvable and you get something non-trivial, then you know that the eigenvector exists for that lambda, and therefore the eigenvector does exist, and you can determine it as well. So the values on a diagonal matrix are the eigenvalues, but you can't ref to get there. So we talked about that, how that diagonal matrix, you can see what the eigenvalues are, but to get there, it's not as simple as doing ref or even just reduced echelon form. And you have to factor it using something called an LU factorization or a diagonalization of the matrix. So it is possible, but it's nothing we've learned how to do. So the main thing I need you to know is that you can't do RREF or REF to get the eigenvalues. And if the determinant equals 0, then that it indicates that one of the lambdas must be 0. And that also kind of means that if your lambda equals 0 for an eigenvalue, then you don't have a inverse. And that's kind of the first piece of that whole idea that the health of the matrix or the behavior of the matrix is discoverable within the set of eigenvalues. That's like the first thing we can do. So if we can find the eigenvalue and we find that one is 0, then we know that there is no inverse. One other thing that I was able to hit in my second period class, but third period missed it. And that is that essentially if you have a bunch of eigenvectors that are linearly independent, that will also mean that their eigenvalues are linearly independent. So if V1 to VR are eigenvectors that correspond to distinct eigenvalues, and that distinct part is key. Lambda 1 to lambda r of some n by n matrix A, then the set V1 to VR is linearly independent. All right. So this is a theorem from 5.1. And it's just a good one to keep in mind because it uses this idea of distinctness. Distinctness means the lambdas are all different. Lambdas are 1, 2, 3, 4, whatever, okay? Can be fractions, can be decimals, but they're all individual. And the reason this is pretty key is because you can have multiplicity in an eigenvalue, and we've talked about it, but I haven't shown you an example of that. You'll see that later in another video. But if you have multiplicity, that means you have a repeating of the eigenvalue. 1 occurs twice or 6 occurs twice. In these cases, in this situation, if you have two eigenvalues that are the same, their eigenvectors will also be the same, which by definition means they cannot be linearly independent. So if you have a set of eigenvectors coming about that all come from a different lambda, then all of those eigenvalues will also have to be linearly independent. So that's a kind of a key document to say that, like, look, all of these eigenvectors kind of do create almost like a basis for the matrix. So that is the summary of 5.1. We did a lot of good problems, so you'll want to review the notes for that. But that will take care of what we need for 5.1. So the next thing that we're going to get into is for 5.2. And for 5.2, we are getting ready to actually solve for the eigenvalues. And we're going to do that using the characteristic equation, which I began to present last time, but I didn't quite finish. So I'm going to bring up a couple of theorems. So these are a couple of important theorems from 5.2. The first two, the invertible matrix. And it just kind of spins off what we discovered. If A is invertible, then we don't have 0 as an eigenvalue, and the determinant of A is not 0. So that's exactly what we talked about in 5.1, so it's just further kind of confirming that. Notice that it has come on with the invertible matrix theorem. The invertible matrix theorem is that thing with that big long list. So they added 2 more to that big long list. And then the other thing is the properties of determinants. They brought this back up because they want to remind you how to do it, because that's how you find the eigenvalues, is through the operations that you use to do determinants, which is why determinants had to come first. And it's ultimately why I wanted to include it on this unit's test. Okay, so we're also going to use these 2 little pieces to help us establish what the eigenvalues are. So I first gave you this equation, and then we changed it into this equation, which was really helpful. And I told you this was the characteristic equation, sort of. And it did allow us to, given a lambda, solve for an eigenvector, so it did help, but it didn't allow us to solve for the lambda. The only way we could possibly solve for the lambda is if I gave you the vector, and then you could. But what if we have none of that information? What if we don't have the eigenvector, we don't have the eigenvalue, we just have the matrix, and we need to figure out the next pieces? We're going to use the data here to help us figure that out. So first, what you have to appreciate is that in any time you have an AX equals 0, you're either going to have a trivial or a non-trivial solution. If the trivial solution is the solution, that means that X is only 0 and that A is linearly independent or has an inverse, has ones down the diagonal. A non-trivial means that we have some sort of free variable, and it goes from there. So in order for this lambda to be significant, it has to have an eigenvector that's non-trivial. So we're looking for these values that don't give us the trivial situation, which means we need something here that doesn't have an inverse. Because if it doesn't have an inverse, it won't be linearly independent, and we'll end up with something other than a trivial X. And if we want something that's linearly independent, or we don't want something that's linearly independent, if we want something that's linearly dependent, then we also want A so that A is 0. If there's no inverse, then A is equal to 0. Versus if A is invertible, A is not 0. So if no inverse, then A is 0, which will give me the non-trivial free variable. And this is how we're going to use this equation to make things happen. If I take AX minus or equals lambda x and change that into A minus lambda I, X equals 0. If the determinant of A minus lambda I is 0, if I solve for when that happens, then what I'm going to end up with is all the possible lambdas that will make a minus lambda I terminate 0. And those lambdas will be associated thus with x's that are non-trivial x values, and those will be the eigenvectors. So this, my friends, is the characteristic equation. And that's what we're going to use in the next video.